Welcome. Let me say something more about coloring of manifolds in 2 or higher dimensions. It's an exciting topic and builds on work which was done in the last century, especially about planar graphs. And so one example of a result about planar graphs is that the triangle-free planar graph can be colored by 2 or 3 colors. But Mycielski a little bit earlier even showed that one can color, that there are triangle-free graphs which need arbitrary large number of colors, and he introduced this operation which preserves triangle-free graphs and which increases the color by 1. It's an exciting theorem. Maybe I explain it quickly, but before that, when we are going into higher dimensions, we don't want to do this embedding into a manifold. That's a completely ill-posed question, because you have to say what you actually mean with embedding and so on. So a purely combinatorial setting is really nice, and there we have a kind of a notion of manifold in dimension q, and we have an upper bound 2q plus 2 for that in the case of q is equal to 2, that would give 6. Right? That gives a 6-color theorem for two-dimensional graph. Two-dimensional sphere coloring is equivalent to the 4-color theorem, as I explained a couple of times already. And what is important in this context is the dual graph. So if you have a manifold, that's a manifold, two-dimensional manifold. The dual graph consists of the maximal simplices as vertices, and then you connect to if they are intersecting in a codimension 1 simplex. What also plays an important role here are the bones. So the bones are the q minus 2 dimensional simplices. In this case, in 2 dimensions, these are just vertices. And then we can look at the Fisk manifold. The Fisk manifold then tells us whether we can color the dual graph with 2 or 3 colors. And that's the theorem I want to kind of, I'm still working on writing this down, that a q-manifold has the property that the dual graph is always colorable by 2 or 3 colors. And that's a generalization of the Grötzsch theorem. And the same proof then also shows that we can color with 2 trees. So that's the vertex abericity, and the vertex abericity 2 is really needed here to color the manifold with 2q plus 2 colors, because we can then just take along a tree, we can color without constraint, without problem, and then we have for every tree we can use 3 colors here, so 6 in total, or 2q plus 2 in general. So let me explain quickly arbitrary large chromatic numbers for triangle-free graphs. What Mycielski did is he takes the graph and he puts a shadow with the same graph and then connects. So for example, there are no connections in the shadows itself, but you connect to the old graph wherever this has been connected. So you connect this with this because there was a connection here. And additionally, the second thing you do, you add another vertex. So if there are n vertices in the original graph, this Mycielski operation has then a graph with 2n plus 1 vertices. And the claim is that the chromatic number exactly increases by 1. So let me just explain that. There are 2 things. First of all, you have to show that you can color it with C plus 1 colors. If there are C colors here, so this has been colored by 3 colors, you can color the full graph with 4 colors. Let me just explain how to do that. So this was the original coloring, the colors here. What you do on the mirrors, you just take the same colors. So you take the same colors here. You mirror also the colors, and then you need another color for that additional vertex here, which is connected to everything in the shadow. So why is this a coloring? I mean, you have just to note that this is still fine because they are not connected here. You have no connection here, and so this is still provides you a color with the same number of colors here, 3, and then you need a 4th color here. Now the other direction is you have a coloring here with C+1 colors. You have to show that you can actually color the original part, the original G graph, which is a subgraph. You can color that with 1 color less. So what you have, you know, here you have an additional color, the blue, this blue color. We get rid of that blue color. How can we get rid of that blue color? So what we do is we color everything, we leave everything with the colors which are not blue. So we leave that. And what we do where we had the blue color, which is the color of W, we just put the color of the mirror. So I'm putting, because it was green here, I put the green here, and because it was red here, I put red here. And you can easily see that this is now a coloring of G without the blue color. So you can get like that a coloring of the original graph with 1 color less. So this proves then that this Mycielski operation just increases the color by 1, and it's also, if this is triangle, if the original graph was triangle free, also the new graph is triangle free. So here's an example. If you take the C5, actually if you start with that, this operation gives you a graph with which is disconnected. So usually ignore this, and then you have that as the kind of, this is can be colored by 2 colors. If you take that, you get the C5, the cyclic graph, which needs 3 colors, and then when you do it again, so you get the mirror inside and the additional W here, which is in the center. So the W here is in the center here. So that's the Grötzsch graph also, which has been found also by Grötzsch. Now, in order to generalize this theorem to higher dimensions, that every dual graph of a manifold can be colored by 2 or 3 colors, I think this is actually can be done in a constructive way. And here I try to explain this in an example. We start with the icosahedron graph, and this is the dual graph, which is the dodecahedron. Just put them here. That's the graph, that's the dual graph. And now we start coloring. And what we do is we just use only 2 colors. So what we try to do, we just use only 2 colors, and we go along these dual bones. So every of the bone here has the dual bones are circular graphs. So in a 3-dimensional graph, what you have is, for example, the bones are edges, and you look at all the tetraeder which hang on that edge. In 4 dimensions, and that's how I got into that again, 4 dimensions, that's in relativity, for example, important when you have 4-dimensional manifolds. So Recke was looking at the bones which are triangles, and then the dual, which is the intersection of unit spheres in unit spheres in unit spheres, are circular graphs by definition, right, of the manifold. In a manifold, the unit sphere is a sphere, and in that unit sphere, which is the intersection of 2 adjacent spheres, you have a codimension 2 sphere. If you take another intersection, you get a codimension 3 sphere. In 4 dimension, a codimension 3 sphere is a 1 sphere. So you're interested in this dual bones, and this is what you see here. These are the dual bones, right? So also in higher dimensions, you see almost these cyclic graphs. You start with the point in higher dimensions, there are much more vertices attached to it. So much more tetraedra are so dimension q, they are q+1, the vertex degree is q+1, it's constant vertex degree q+1. By the way, this graph here, this doesn't preserve regular graphs, so the vertex degree increases for some vertices more, like at least n. So that's it's actually exactly n. So you can, but n is the number of vertices of the original graph. So the idea is, if the dual bone has an odd number of vertices, then we get into conflicts. If there's an even number of vertices, we don't have conflicts. So if you don't have conflicts, then we can color with two colors. In this case, we already get a conflict here. Actually, this is kind of almost the worst case. What we have is conflicts in every of the dual bones, because every of these dual bones have length 5. And so what one does, we just color it with blue and yellow all over. We accept some conflicts locally, and we always then at the boundary we take a point on the boundary where we have a conflict, and we start extending again, and then we get again a conflict somewhere on the boundary. But these conflicts are always, in distance, so that you can always continue, and you get the coloring of the entire dual graph. I have still to write this down. This is for today.